Welcome to Module 1, an introduction to MADARA and GAMS. In this talk, we will talk about the SEI-developed, open-sourced, freely available, multi-agent distributed adaptive resource allocation project called MADARA and the Group Autonomy for Mobile Systems project called GAMS. MADARA and GAMS have been used consistently at SEI and the CPS-ULS group to provide predictable execution and knowledge sharing between a group of distributed autonomous systems. Before we get into GAMS, let's first talk about MADARA. MADARA is a thread-safe world model for automatically updating agents in your network with what's going on around them, their own internal self-interested state, as well as the state and interest of other agents. Information like robot location, orientation, where they're at, their status in the mission, things like that. So MADARA provides you with a consistent worldview of what exactly is going on in your mission. MADARA first started development in 2009. At first, it focused on knowledge and reasoning, Boolean logic, and reinforcement learning, the basic building blocks of machine intelligence and machine learning. Over the years, it has grown to support things like generic distributed systems, threading, advanced quality of service, UDP-based transports, Java, Android, and Python support. The focus of development since 2009 has really been on quality of service. We haven't been focused on making a research platform or a research middleware. We've been focused on making a production quality middleware that helps you accomplish your own research. This means focusing on scalability, speed, expressiveness, documentation, and an open source release process, a BSD-style license process that allows you to freely open, use, and edit the software for your own purposes. This includes extensibility for threading, transports, and programming models, such as iterative versus reactive, event-based programming, if you will. MADARA is the larger of the two projects between MADARA and GAMS and has been developed for longer. In the code base, you're looking at about 110,000 lines of code with about 45,000 lines of commenting. The next thing we'll talk about is GAMS, the Group Autonomy for Mobile Systems project. GAMS provides the portable logic and algorithms that interact with platforms in your robotic systems. You can think of GAMS as an interface for portable AI. Essentially, if you write something in GAMS, an algorithm in GAMS, then you'll be able to port that algorithm to any other type of robotic system or simulation platform. GAMS first started development in 2012 and was built directly on top of MADARA. It was originally intended to support distributed algorithms for quadcopters in outdoor environments. But over the years, it became important that we support extensible algorithm infrastructure so we could add whatever algorithm we needed to for any kind of mission-focused autonomy, as well as extensible platforms so we could support things like boats or ground robots, advanced quality of service, generic simulation environments, multi-step and dynamic algorithms, and ports to Java and Android. The focus of development throughout the process has been very similar to MADARA. We focused on quality of service, time and control, scalability, speed, and expressiveness. We also made sure that there was an open source release process, a lot of documentation, and extensibility for new platforms and algorithms. GAMS is the smaller of the two projects we're going to talk about today. There's about 55,000 lines of code and 32,000 lines of documentation, so almost 100% here. We're looking at about 66% is commenting to help you understand what exactly is going on in the software. Before we talk about GAMS, let's first talk about how you're supposed to use MADARA. The way you use MADARA is that you interact with a knowledge base. The knowledge base is essentially that world model that we talked about earlier. Anything about your mission, anything about your location, orientation, whether you're a software agent or a robotic system, will be populated in the knowledge base. After it's in the knowledge base, the transport layer transfers that knowledge across the network so other people understand what your world model has been updated to or how they're supposed to interact with you in the setting of the real world. The threader controls portable, knowledge-enabled threads. This allows you to have an executable unit with quality of service attached to it that also provides you with a knowledge base. GAMS is built on top of MADARA, so it inherits all of its features. You can see that as part of the GAMS process, you're going to interact with a knowledge base, a threader, and a transport, just like you did programming a standard MADARA application. But you're going to create a user application that features an autonomous system controller. This system controller executes a distributed algorithm in what's called a MAPE loop, monitor, analyze, plan, execute, with knowledge. Essentially, in the monitor phase of your loop, you're going to be sensing around you. This is usually done on the platform layer. You're going to be analyzing what you've seen in the environment, planning your next actions, and executing them in that way. The algorithm interacts in a standard interface with a hardware simulation platform. This allows you to build a distributed algorithm that's portable to any platform or simulation environment. Let's talk about the platforms and uses that we have targeted for GAMS. In 2013 and 2014, we focused on quadcopters in outdoor environments, 3 to 5, maybe 10 quadcopters working together towards a mission-focused autonomy, such as searching an area, surveillance, or helping find people in search and rescue situations. In 2015, we focused on making sure everything was scalable and that you had adaptive algorithms that could essentially look at the environment around them and change what they're supposed to do. In our scalability experiments, we saw that we could do hundreds of thousands of hertz, hundreds of kilohertz in processing power just from updating our world model and seeing what we can do with mission-focused autonomy. This means that you can basically scale the number of agents in your system, whether it's in a cluster or whether it's outdoors, to thousands of agents communicating together. Other platforms and uses for GAMS include adversarial algorithms, which we did in 2016, and also real-time simulation infrastructure for verification techniques like DART and Demeter. These are technologies we may talk about in a future module. We've also been targeting space systems with GAMS, including the multiplanetary smart tile system, which is supposed to scale to hundreds of thousands, if not millions of smart tiles floating around in space, communicating and harvesting energy. MADARA and GAMS are not the only types of software you can use for building robotic systems or software agents that are self-interested. The major industry player in this space is actually ROS, the Robot Operating System. The pros of ROS are that it's also open source, available at ros.org. It has commercial support and a very large active development community that has lots of available tools. The cons of ROS are that it forces message passing as a main programming interface. You have to figure out how to make an emergent system in robotics. This does not scale well in processing hertz of number of agents. It also forces synchronous interactions that can block indefinitely. For instance, if you aren't able to communicate for a long time, you could have a message queue that backs up and you can't send anything else until you finally do get in contact. It requires a reliable network transport that may fail spectacularly when networking is unreliable or offline for long periods of time. This could occur in natural environment problems or adversarial jamming. It also features a lack of verification tools. It was not designed for verification. We will be using GAMS and MADARA in this tutorial series. Most high-level autonomy programming concepts translate to programming any autonomous system, including the ROS system. The next steps in this tutorial are that we're going to install MADARA and GAMS, then we're going to use the GAMS project configuration tool to make our own distributed autonomy projects, and then we're going to create a distributed algorithm that you can run on your own computer.